Hey everybody, Dr. White. Continuing our discussion of sequences and series, but we're going to back off of infinite series for a moment and talk about polynomials, using them to approximate functions. So for example, say you've got this function like f of x is natural log of x. It's tough to find the values of natural log of x. There ain't no simple arithmetic there. And so you might want to approximate those values using some function that is easier to compute with, but which is close to natural log of x. And so you may remember linear approximations from Calc 1. Look at this graphical situation here. Got this function log of x, and maybe there's this number on the x-axis, call it a, that I would like to find values for log of x nearby that value of a. Log of 1 is 0, as you can see from the graph, but like if you wanted to know like log of 1.03 or log of 0.97, that would be really tough. But maybe what you could do is, instead of work with log of x, you could work with a linear function that approximates log of x really well near a equals 1. Let's call L of x the best linear approximation to f of x near a equal 1. Here's a graph of what it might look like. What should it be in order to be the best linear approximation? Well, okay, let's set up that question by thinking of L of x as a linear function. So it's like mx plus b, where m and b are real numbers. M's the slope and b's the y-intercept, And what should the m and the b be? Well, I think that two things need to happen, and they're illustrated here in the graph. First of all, the line had better agree with the graph of log of x at a equals 1. Secondly, it should have the same slope as log of x does at the point a equals 1. So I've drawn this L of x here doing that. We just need to find like what should the m and the b be in order for that to happen. So two things I need. I need that L of 1 has to be f of 1. And L of 1 would be what you get by plugging in a 1 for your x. And f of 1 is log of 1, which is 0. And so you get the equation m plus b is 0, and that might be useful. Now, the other thing is that the slope of the line ought to be the slope of the curve at the point a is 1. Now, the slope of the line is L prime, so I'll just get L prime and I'll plug in 1. And the slope of the log of x will be f prime of 1. Okay. So L prime of x is pretty easy to find. You just take the derivative there and, well, it's m. No surprise there. Now, the derivative of log of x is 1 over x. And so L prime of 1 is m. F prime of 1 is what you get by plugging a 1 in here, and that's a 1 over 1. So we're getting that m is 1 over 1, so m is 1. And we also had that m plus b is 0, and we can use that now. Just put in that m is 1, and we get b is minus 1. So the best line to approximate log of x with, when you're working near the value 1 on the x-axis, is x minus 1, 1x plus negative 1. Now, I want you to observe that you can write that L of x in this way as 0 plus 1 times x minus 1. And that turns out that, 0 is log of 0. And, 1 is the derivative of log at x equal 1. So you've got this form that you may be familiar with from Calc 1 for the linear approximation to a function near the value x is a. It's f of a plus f prime of a times x minus a. Okay, so the idea of approximating a function with a line is something familiar way back from Calc 1. But what if you wanted better approximations than what the line could deliver? After all, the line's going to be perfect only when the x is equal to the a. Once the x, like maybe out here, drifts far enough from the a, the line's height is going to be pretty far from the curve's height. And so the approximation won't be as good. So could we maybe, at the cost of a little bit extra complexity, get better approximations? For example, could we, instead of using a line to approximate, could we use a parabola to approximate? A parabola is the graph of a second-degree polynomial. Could we use a second-degree polynomial to approximate f of x near x is a? I have a suggestion for what it ought to be. I'm going to call that second-degree polynomial t sub 2 of x, okay? 2 for the degree 2. I suggest that it ought to be this. So it starts off the same as the linear approximation, L of x, but it adds on a second-degree term. See this second power of x minus a? The coefficient has a second derivative of f at a, but there's also like a 2 at the bottom. And so you may wonder, like, why do I suggest that as the way to finish off this second-degree polynomial? Well, here's why I'm suggesting this. I first want you to notice that at x equals a, t2 is exactly what f is at a. I mean, just plug in an a for the x here. You'll have an f of a here. You'll have an a minus a here, 0, and you're going to have a 0 squared here, so you're only going to get the f of a out. And so this polynomial has the same value as f does at x equal a. Let me take the derivative of that polynomial. It's this. You see, f of a, that's a constant as far as x is concerned, so its derivative is 0. And then when I take the derivative of this term, I've got this constant times the derivative of x minus a, and the derivative of x minus a will be a1. And so all I'll have is an f prime of a off of that term. And when I take the derivative of this third term, I'll have this constant times the derivative of x minus a squared, which is twice x minus a times, says the chain rule, the 1. And so there'll be some cancellation. The 2 will cancel with the 2 on the bottom, and you'll only have f prime prime of a times x minus a to the first power. Okay, and so then just take that derivative and plug in a for x. You are going to get a 0, oops, let me fix that width. When you plug in a for x, this will be a 0, because you'll have an a minus a right here. So you'll only be left with f prime of a. So that's saying that the slope of the polynomial at x equal a is the slope of the f at x equal a. So not only does the polynomial have the same value, it has the same slope at a. But there's more. Take the second derivative of this polynomial. So here's the first derivative. Let's imagine its derivative. This is a constant as far as x is concerned, so we only need to look at the derivative of this constant times an x minus a, and the derivative of that will be that constant f double prime of a. And so that's saying that the second derivative of the curve is the same as the second derivative of this polynomial at a. So remember, second derivative, it tells you whether something is concave up or concave down. When the second derivative is 0, there's no concavity there, it's like straight. It's measuring how much bend there is at a. That's what the second derivative does. And so we're learning that for this particular polynomial here, it's got the same value at a, it's got the same slope at a, and it's got the same bend at a. it ought to be a better approximation to the curve f near a. Let's see what that polynomial is. So if I'm going to see what it is, I've got to get this, you know. So start with f of x is log of x, and I take its first derivative, and then the next derivative is negative 1 over x squared. So when I look for f double prime at a equals 1, when I put in a 1 here, I'll get a negative 1 out here. And so when I plug into this, I'm going to have my same old 0 plus 1 times x minus a, but now I'll have a negative 1 over 2 times x minus a squared. So I've got that same linear approximation plus minus a half x minus 1 squared. Okay, what would be the best 3-degree polynomial to approximate f of x near x equal a? I think you might be able to figure out where I'm going with this. I'm going to set up a 3-degree polynomial which has the same value at a, the same slope at a, the same second derivative at a, and the same third derivative at a that f does. And my suggestion is this. Same as the T2 plus this constant times x minus a cubed. So it's third derivative at a, but I'm dividing by 3 factorial. Okay, let's see why I chose that. Well, run through the same calculations as before. If you plug in a to T3, you'll see that it's f of a, so it agrees with f at x is a. If you take the derivative and then plug in a, you'll see that T3 has the same slope as f does at a. If you take the second derivative and plug in your a, then you'll see that T3 has the same bend as f at a. If you take the third derivative, you'll be down to just the third derivative is that constant. And that's because as you've been taking derivatives all the way along, you are accumulating like powers. Like here was the first derivative and there was like a 3 that came down. And the next time you took the derivative of that, you had to take this derivative of x minus a squared. There was this 2 that came down because of that. And then the next time you're taking the derivative, it just goes away. I'm sticking a 1 here because that's the derivative of x minus a. Okay. And so, fit the width again. And so you're down to this constant, which happens to simplify to just the third derivative at a. And so this third degree polynomial has the same third derivative as f does, the same rate of change of the second derivative, the same rate of change of the bend. Some people call that the jerk. It has the same jerk as f does at x equals a. And so that ought to be like an even better approximation than T2 was for log of x near the value, a. In fact, if you go ahead and try this out where f of x is log of x and a is 1, then you're going to get this polynomial here, the same old T2. You just got to figure out this coefficient here. And so you say, okay, I need to find the third derivative at a, the third derivative at 1. So I start with my function. I do a first derivative, I do a second derivative, I do a third derivative. I plug in a as 1, and when I plug in 1 to this, I'm going to get a 2. And so the coefficient there is supposed to be the third derivative at a over 3 factorial. That's 2 over 3 factorial. That simplifies to 1/3. So I'm claiming that these approximations get better the higher degree that you use. it's probably time to see if this is really working out that way. So why don't we approximate the log of 2? So we're trying to find the log of x when x is 2. Now 2 is a unit away from our center of a equals 1 that we're working around. So that's not really near at all. But let's just see how this goes. So I try L1 of 2. That's the linear approximation. I'm just going to call that T(1) of 2 because it's a first-degree polynomial. And so that was the 0 plus the 1 times x minus 1. So I plug in x is 2, and I get 1 out. Okay, and let's see what that second-degree polynomial would have done. And so that's the linear approximation minus the 1/2 x minus 1 squared. And so I put in x is 2 there, and I'll get the 1 from here minus a half, which turns into a plus 1/2. And let's try the third-degree polynomial at 2. And so I've got my second-degree polynomial, which is a half, plus a third. 2 minus 1 cubed is a third. Half plus a third turns out to be 5/6, which is 0.833333 forever. Okay, and so let's see, how does that do? How does that do as an approximation? Well, on my calculator, I looked for natural log of 2, and I got 0.693, which is not so terribly close to 0.833 repeating. Well, I wasn't really very near there. Let's try something that we feel like is near. What if we wanted to approximate log of 1.1? Now, 1.1 is definitely looking kind of near 1. On a calculator, I found that log of 1.1 is about 0.09531,018. And I went and found my polynomials, the linear, the second degree, and the third degree at 1.1. And I will not bore you too much with the calculations, but you'll notice they are kind of leveling off pretty quick. This is 0.1, here's a 0.995, and here's a 0.9953333 repeating. And when we look at that compared with what the calculator said, you see much better agreement. That's agreement to all the way out to the 4th decimal place. So that's looking pretty good for the idea of using a higher degree polynomial to approximate a curve when you need to compute some of the curve's values. So it's worth it to just make a general definition about this. Let's define the nth Taylor polynomial, call it T sub n, of a function f of x centered at x equal a. Okay, so you take a function f, it needs to have a lot of derivatives. These derivatives need to exist. And you're planning to center around some point a, get approximations near x is a. T sub n of x is defined to be f of a plus the first derivative at a times x minus a, the linear approximation. I'm just going to write a 1 factorial there to get a pattern going, because 1 factorial is just 1. And then the next thing we had was the f double prime a over 2. I'm going to write a 2 factorial to get a pattern going, times x minus a squared. And you would keep going like that until you decide to stop somewhere. And the general term is the nth derivative at a over n factorial times x minus a to the n. So actually, if you wanted to write the nth Taylor polynomial in summation notation, you could. It looks like this. Sum k goes from 0 to n, k's derivative at a over k factorial x minus a to the k. You can see that this term fits it and this term fits it all the way up. Even this term fits it where k is 0, because the 0th derivative, like if there were a 0 here, the 0th derivative of a function is the function. And so that would just give you an f of a. 0 factorial is a 1. x minus a to the 0 is a 1. You really would only emerge with f of a at the k equals 0 term here. So this is a way to write it in summation notation, if you like. And what seems to be happening is that the bigger the degree n that you use, the better the nth Taylor polynomial is going to approximate the function, as long as you stay kind of near x equal a. So let's look at this graphically. I've provided a link to a little app that uses the geometric software called GeoGebra. It's over in Canvas. Let's visit it. So I'm going to Canvas here, to the page for section 10.7, and I've got a little link to this app. So, well, let's open it up. There we go. So it takes a moment to load, I guess. And what I want to do is I want to change my function. I would like it to be natural log of x. And I would like to change my center to be at a equals 1. Okay. And there we go. And so right now it's giving me the 0th Taylor polynomial. So that would be just the constant log of 1. It'd be the f of a. And so that's just log of 1, and log of 1 is 0. And so this dotted line that you see graphed here, that's the t sub n of x this time. It's the y equals 0 line. All it does is agree at, why am I doing this? All it does is agree with the value of f. It doesn't even agree with the slope. But let's go up here to the slider and let's bump it up. Now we're looking at the first Taylor polynomial. And so it has that, the formula x minus 1 that we found. And so there's linear approximation. And now let's bump this up again to a second degree Taylor polynomial. And so you can see that minus 1/2 x minus 1 squared got added on there. And so here's this parabola that has the same value, the same slope, and the same bin as log of x at x equal 1. And it looks like it's going to do a pretty good job as long as you stay close to x is 1. Okay, let's go up to the third degree polynomial. And so third degree polynomial, that's the dotted line graphed here. And you can see that it's almost indistinguishable from the log of x as long as you're pretty near the x equal 1. And so you can actually just look at further higher degree polynomials if you like. Here's the 4th degree polynomial, the 5th degree, the 6th degree, the 7th degree, and the 8th degree, and the 9th degree, and the 10th. And I'm just going to bump it up as far as it'll let me go. So there's the 30th degree polynomial. And wow, there's almost no distinction between the polynomial and the curve for quite a ways around the center of 1. So that's pretty impressive. I really like that. Here, I'll reload and get the original. We might come back to that a little bit later. So I should say that it's very common to, when you make your Taylor polynomials, to center around a equals 0. Now you can't do that when you're trying to approximate log of x, because log of 0 is undefined. But for a lot of other functions where the function is defined as 0, it's just common to center at 0. And then your Taylor polynomial will look like kth derivative at 0 over k factorial. X minus 0 to the k would just be an x factorial. Sum that up, k goes from 0 to n. When you're doing that, you're making what are called the MacLaurin polynomials for f. So we'll be looking at those quite a bit, along with just more general Taylor polynomials. This is probably a good place to stop in the screencast. And when we get together next time, we'll just try computing some Taylor and MacLaurin polynomials for a few other functions and see how they do in their work of approximating. See you soon.